We agreed that it would be complete. So as you can see here, this is its part, and this is its part. Here, as an engineer, your circuits must have a storage source here, and a storage source here, meaning this is from, and that is completely different. Okay, if both are from two different MCBs, both must also have their source coming from the DC-DP, which is the DC distribution board, from two different sources as well. This means one is from one bus and the other is from the other bus. So that if I get both from the same place and that source fails, I would lose the tripping in this circuit. For all the breakers I have, or at least, for example, if I'm talking about my breaker, this is for trip circuit 1 and trip circuit 2. In this case, I wouldn't be able to open the breaker either through trip circuit 1 or through trip circuit 2. No, I would be able to open it, and even if a fault occurs, the breaker won't open because of this. That's why it must be from this and that. And also when I come here, each one of them must be completely different. Okay, this is my tripping circuit. Before I go to it, I will draw it for you first by hand. And after we understand it by hand, we will go back to our circuit. All right, let me open PowerPoint, which is in front of me, but you won't be able to see it if I open the circuit. I can do it, or let me make sure this table is visible to you. Okay, let me enlarge it or zoom in on the screen. I think now it's clear. I think you can see the screen is zoomed in, right? All right, engineers, let's delve into the fascinating details of how this tripping circuit operates. It's quite an interesting process. Very good. We will now proceed to discuss the intricate workings of the circuit breaker tripping circuit. This involves understanding the mechanisms that trigger the circuit to trip, ensuring safety and preventing overloads. By examining each component, we can appreciate the engineering behind it. Circuit breaker tripping. What? Tripping circuit. All right, okay. Engineer, how does this work in simple terms? Now you have your DC coming in. Here's the positive coming from the DC panel. And down here, what do you have? Down here, you have your negative. Is that clear? So what is this? The positive. And what is this? This is the negative. Got it? You said it's nice. I also told you that here you have your trip coil. And this is its trip coil. And we will call it trip coil 1. And you have an exactly similar circuit for trip coil 2. Very good. So what happens now, engineer, is that you might have here like this. You might have a situation, for example, an emergency, and then you have something like that, or you might have something coming to you, right? So you have three different things that might be coming to you. Okay. From the protection, but through 94, which is the silver set, and it might also be coming to you as a trip from the protection, but through 86, which is the lockout. I've sent you the ANSI code, and by the way, the handout that I wrote by hand gives you only the ANSI code relevant to your task within the switch gear, even with your protections. This is in case you don't want to refer to the ANSI code, which is the meter number included in it. I have already provided you in the handout with only the specific part. Okay, and here, what could it be? Of the circuit, what? The circuit breaker. Okay. Okay. So what's happening? What's happening now is that he's saying he's afraid now that I've connected all these things to the balance, for example, like this. Okay. Connected like this in parallel in this way. Okay. Very good. He's afraid now that if the supply cuts off, if the supply cuts off, I don't see that there's a problem for me. Okay. Okay, if I put this supervision at the end of the circuit, this supervision monitors the positive from above and the negative from below. So if there's a problem with the trip coil, if there's a problem with this contact, will I know? No. Okay, if there's a fault, will the breaker open? Also no. So what's the solution? Okay, let's see together. He said quite simply, we'll do it the old way. We as engineers will come here. Okay, we enter the terminal block, and from the terminal block, we enter our contact. And we exit from the head of our contact to another terminal block, and we exit from it like this, okay? We come here and enter here into a terminal block, okay? Until we go where? To the head of this contact. Exit from the head of the contact. From the contact itself, not from the terminal block. To what? To another terminal block. And I will come here to a terminal block, and I will also come from the head of the contact and return here, okay? Very nice. And then I will come here and put a coil for you called what coil? Okay, very nice. And here's the coil. I returned with it, leave it. I intentionally left this open I come here to a terminal block like this and exit like this. And I will come here like this, also a terminal block like this, and exit also with a terminal block like this. And I will come here like this, exit to a terminal block like this, and also exit here like this with a terminal block. And I will come here to what? To the trip coil. Okay, Engineer Rashad, what did I gain? Focus with me. Now the idea is quite simple. The coil, what's its current state? Now it will receive a positive from here, like this, like this, like this, until it reaches it. Until the positive reaches it, okay? So the positive has passed through all this wiring. Therefore, any cut in this path means the coil won't receive the positive, right or wrong? You told me right. Okay, this means that it monitors the entire path, right? That's why this entire path, look how it goes. It goes up to the contact head and exits from it, the contact head and exits from it, the contact head and exits from it. So I am assured of my wiring from the positive up to the head of each contact. Imagine, my friend, if instead of returning from here, I return the wire like this from here. All right, in this case, let's assume this wasn't there. This wire wasn't there, and I was returning from here. Let me draw it for you on the side. For example, here it is. Imagine if this was the positive, and I come here to this contact and exit here with a block like this, showing the regular DC, and I come here to coil A. Now, if the wire going to the contact itself is cut, coil A wouldn't lose the positive. The positive would continue normally, right or wrong, right? So it wouldn't perform what? It wouldn't perform complete supervision. That's why this is wrong, and I start monitoring up to the wire from the head of the contact. This is correct, Aquis, and this is wrong. So, where does the monitoring take place? It takes place from the head of the contact itself. Just to make sure I'm explaining clearly, can you see this image zoomed in the middle of the page, or do you see it small like when you see me talking? Is everything clear, or does it seem distant? Okay, the engineer said, okay, and that's it, everything is clear. Okay, very good. All right, so the first thing we notice is that when this comes to us in the drawing and the contact wire is connected here like this, we adjust it here because this is your standard and these are the requirements of SEC, Aramco, and anyone else in the world that the monitoring is done up to the contact head itself. Very good. So I am reassured through monitoring. Now, this is a coil that will monitor the positive, right? And it will also monitor the wiring up to the head of the turbine contacts. Is that good? Good. Now, as for the negative, Engineer Rashad, let's take a look at the negative. The negative will come like this, pass through and find a coil here. All right, it continues after the coil like this. And it also goes up to the head of the contact from below. So if you summarize this circuit, what will it be? It will be a wave, right? And there's a wire, which is the loop wire, until it reaches the coil. And then on the other side, it's all wire until it reaches the trip coil. All right? And then you have the negative. So which coil is this? It monitors all the wiring you have in the positive direction and also monitors the negative, but through what? Through the trip coil. So it monitors everything like this. The positive loop and monitors the coil itself. Oh, sorry. It monitors all the wires up to the contact and monitors the positive itself and the negative itself and monitors the wires from the negative direction and also monitors the trip coil. That's why in this case it's referred to here not as DC supervision, but it's called a trip circuit supervision. Exactly. And be careful because many people and even experienced engineers might tell you it's called TCS and they might say it's trip coil supervision. No, it doesn't just monitor the coil. It monitors the entire circuit. It monitors the positive by passing through all the wires, and it monitors the trip coil and the results and all the wiring from the other side. You said, okay, and I told you, okay, all right, Engineer Rashad, can you give me a little more? Go ahead. Now, Engineer Rashad, I'm here, right here. If I give an open command to the breaker, meaning I've selected the emergency position and given an open command to the breaker, doesn't the breaker's trip coil activate and trip the breaker? I told you yes. Okay, what if I give another trip command again? I gave another trip command. Okay, if I give another trip command in this case, what will happen is the trip coil will still receive a positive signal as it is already connected. It will receive a positive signal again. Okay, Engineer Rashad, isn't it the same as the closing coil? Isn't the closing coil when it receives the positive signal multiple times? And as a result, the breaker remains open, like here, for example. The breaker is open. So what will happen? What's new? There's nothing new because the breaker is open, right? So the arrival of the positive and negative to the trip coil will still cause it to draw current. For example, from 2.5, in the case of a switchgear medium voltage, up to 3 amperes, right? That's the current. And thus, it might move. That's why I'll do the same action I used to do with the closing, which is the interlock topic. So here, I will use a contact here, 52A, God. Okay, because Rashad, in the interlock there in the closing, I used to use 52B, right or wrong? Here, why 52A? Let's go back to Rashad. He told us, we said the drawing standard says what? It says that the breaker is drawn with all its contacts in the state that the breaker is open, right? So if the breaker is open, what's with this contact? I need one here to be open. Why? So that DC doesn't reach here again. Unlike the closing is closed because the breakers are open. So it is prepared to receive a close command. When it closes the 52B, they would open, which is this one. This was supposed to open, meaning now the breaker is actually open, which is its normal case in the drawing. So this contact was supposed to be normally closed, right or wrong? So when the breaker closes, it opens. Here in the tripping, I have the breaker already drawn in the drawing as open. So when the breaker closes, this closes to allow you to open it. When the breaker is open, this opens. This is considered like the interlock idea in the closing circuit. All right, very good. Okay, Engineer Rashad, add another part for us. I'll add another part for you, Engineer Rashad. Now, if there's no tripping, nothing at all, here's the DC going like this, going like this, going like this, reaching up to here. This is the positive. Then there's a wire going like this, up to here. The breaker is closed. Yes, this code is closed. Trip coil, then negative was cut. So in the end, Engineer Rashad, I will see something like this. Right, I told you, right. Okay, Engineer Rashad, this is 125 VDC, correct? You said it correctly. Okay, engineer, these are coils, and this is a coil, and both are in series. So the voltage is divided between them based on the resistance of each one, right? You told me right. Okay, those who attended the breaker maintenance course with us, or generally, if you know, you now have a trip coil that can operate at low voltage values. We used to test the tripping of a breaker at 70% of 125 VDC. That's fine, very good. And we ensure that the breaker opens and its behavior is correct, meaning it opens and our timing play is good. That's good, okay. Engineer Rashad, suppose the voltage here is divided between these two. For example, this one takes 40 volts while the other takes 85 volts. In this case, the breaker will trip, right or wrong? I told you right, okay? And is this required? No, of course not. Why? Because this is used for monitoring, meaning its role is to monitor and not to cause a disturbance or deliver power to the trip coil under normal conditions to make the breaker trip. That's not its purpose, to send a trip signal. Those who open the breaker, their whole story is to monitor. Just like you have a guard for your building, this guard monitors but does not disturb the people present, right or wrong. His only issue is to monitor, or his task is only to monitor. So here, it's the same story for us. Okay, Engineer Rashid, what about this coil? So what about this coil, Engineer Rashid? The resistance of this coil must be greater than the resistance of the trip coil, which is this one. To ensure what? To ensure that there is a voltage drop here so that the quality reaching the trip coil here, the remaining quality that reaches here is lower. What does this mean? If you have a resistance here and a resistance here, and you apply 100 volts to them, and this resistance is 1 ohm, and this resistance is 1 ohm, 50 amps will flow, so you will have 50 volts here and 50 volts here, right? I hope I'm not mistaken. Very good. Here you go. 50 volts and 50 volts. So what if I make this 4 ohms? What will happen? The 100 volts will carry 20 amps in this case. Here you will have 20 volts, and here, how much will you have? 80 volts. So the more the resistance increases, the more, it takes a higher share of the voltage. So if I increase the coil resistance, what happens? It takes a higher share of the voltage and gives less voltage here to the trip coil. Okay, great. Oh, sir, I testify. What do you think if I make this coil have a large resistance so that it takes, for example, let me give you an example, 90 volts, nice. So here it would be 35 volts. I'm telling you from my place here, 35 volts won't make the breaker trip. Excellent, that's good. So I make this one's resistance greater than that one so that it leaves only 35 volts to reach here. No, be careful. What I'm telling you is wrong. Why? because those 35 volts won't make the trip coil work. But focus on the word but. Those 35 volts will make it draw current. Even if that current is less than 2.5 amperes, it will make it draw current, right? Am I wrong? And this current is flowing continuously, and the breaker doesn't open, meaning the contact doesn't change its position. It will remain closed because the breaker is closed. The breaker hasn't opened, and the trip coil keeps drawing our current continuously. So instead of it being, if it draws 2.5 or 3 amperes for 5 seconds, it will burn out. Right now, it might be drawing only 0.5 amperes, but you're leaving it continuously, man. After an hour, after 2 hours, after 24 hours, after a month, it will burn out because the breaker is closed and keeps drawing the current continuously. It will keep heating up. It's not normal for it to draw that current, right? Am I wrong? Yes. So I need to put a resistor or a coil here with high resistance to ensure that the voltage reaching here is low. Actually, in stations, you're talking about around 5 volts, sometimes even 4 volts, just enough to reach the trip coil. That's why we find that this coil is in series. In series, the resistance is usually 3,000 ohms. Typically, the trip coil has a resistance of about 100 ohms or something like that, or 200 ohms. Here, we add a series resistor of 3,000 ohms to create a large voltage drop, so that the voltage reaching the trip coil is around 5 volts, 4 volts, something like that. The voltage here is not enough to trip the circuit breaker, nor is it enough to allow a large current to pass through here. It's not forgotten. There you go. So you also know what. So that you also, I'm telling you that I have explained it to you, you will find that I have written this here. Exactly. I mean, I have written for you that the use of resistors here, exactly. I have written for you the use of resistors to ensure that my voltage does not reach the trip coil during the square process, to prevent tripping, and also to ensure that the trip coil does not burn out in case my voltage is insufficient to cause a trip, but allows current to pass through the trip coil, which might heat up and burn out. It might heat up and what? Burn out. All right, guys? So let's be aware of this resistor concept. Some of the relays or devices used like this one have a built-in large resistor, while others rely on an external resistor like this 3,000 ohm resistor. How nice is that? Engineer Ershad, you've explained this topic to us, and it's very nice. If the breaker is currently closed, the positive will come from above, pass through the wire to each coil, and the negative comes from the trip coil, passing through like this to each coil. Now, if the breaker opens, Engineer Ershad, before I tell you the breaker opens, what does this coil do? There is another coil called coil C, all right, which has a negative on it. And here's its post. It receives a contact from coil A here. All right, great. So if coil A is intact, it closes its contact here, activating coil C, which means everything is fine. Coil C has something called a flag, like a little flag. All right, they make it like this, an orange colored flag. There it is. It's like there's a round thing, and this round thing has a flag raised. As soon as this contact opens, what happens here is that it lights up red. So you understand that you have a problem. We call this the flag, something like a signal to let you know there's an issue. As long as this wiring has positive and everything is fine, and as long as we come to you through the trip coil and everything is fine, at that time, this coil is working, so it closes its contact. For coil C, everything remains fine for it until there is a break in the DC. If there is any weakness in the wiring here in the positive direction or in the negative direction, or if the trip coil itself burns out, or if this contact has a problem and opens, or whatever the case may be, coil A will immediately open its contact. Coil C will drop off and your flag will go down immediately, indicating that you have a trip circuit supervision alarm. This means that the trip circuit is not qualified to disconnect the circuit breaker. Great, guys, that's nice. So far, everything is fine for us. Okay, now I've opened the circuit breaker. So what happens to this contact? It opens. Well, coil A will give you an alarm saying there's a problem with the trip circuit. That's why I do something else. I bring another coil called coil B. I'm building this with you. I could have told you from the beginning that the trip circuit consists of more than 3 coils, but I prefer to show you the problems and So he brought another coil called coil B. He said that if the breaker is open, then here you use a normally closed contact called 52B. If the breaker is closed, this is closed and that is open. When the breaker opens, this returns to normally open and that returns to normally closed as it was. That's great. So he said, I also want to monitor this. How will I monitor it? I want to monitor all this wire here. Just keep going, going. Here it is. Keep going until I reach this point. Isn't this open now? I'll come from the top of this contact and go here to coil B. And then I return from coil B here to the 52B and then back here to the trip coil. So in this case, when the breaker was closed, it was coil A that was monitoring the trip circuit, right? In the case of the breaker being open, now focus with me, here's the positive, right? And wiring until I reach coil A. This is wiring until I reach coil A, which has a resistor with it, and then wiring, here it is. And then I went like this, and went to coil B, and then I returned from coil B to the trip coil, and then went to this point. So I monitored the entire circuit, but here in the case of the breaker being open, both coil A and coil B are monitoring the breaker in the case that the breaker is, or they are monitoring the trip circuit in the case that the breaker is open. Okay, very nice. So if you have the breaker closed, only coil A is the one that remains active and monitors the circuit. In the case of the breaker being open, both coil A and B are active and monitor the circuit. All right, very good. So, engineer, now regarding coil A, if I open the breaker, okay, if a trip occurs through 94 and the breaker opens, that's also fine. But suppose a trip occurs through 86, what about this contact? It will be closed. If this contact is closed, no one will notice it except you. When you come to check it manually at the station, this means that the positive will come this way, but nothing will go that way. Why? Because this contact is closed, which means there is a short here, right or wrong. So nothing will go to coil A. What coil A? It has a short circuit, that's it. The DC will come this way and go to coil B and return from coil B to the trip coil. So if the breaker was open due to a trip through 86, which is the lockout relay, in this case, coil B alone will monitor the trip coil, right? Or am I wrong? Coil B is now monitoring the trip coil alone. Yes, meaning it is in series with it alone, right? You told me yes. So as long as it is in series with it alone, please also add a resistor. When both were in series, I was satisfied with this resistor, but since there is a possibility that coil B is monitoring the circuit alone, it also needs to have a resistor of about 3000 ohms. Why? To create a voltage drop so that the quality reaching the trip coil is maintained when the breaker is open, but it reaches with quality. The quality could potentially burn what? It could burn your coil, right, guys? Very good. So here you have this 3000 ohms also because the circuit is in series, right? In series with it. Okay, so this means it is monitoring the circuit alone, right or wrong? You told me right. This also means it needs to have a contact here for coil B. So naturally, if the breaker is closed, coil A is alone and monitoring, and the contact is obviously closed so that coil C tells you everything is fine. If the breaker is open, both are closed to tell you everything is fine. If there is a trip through 86, coil A is open, this is open, but this is closed to tell you everything is fine. Anything else means that things are not okay. So if you look with me here at the table that I have made for you below, I am telling you here and here is a condition, and here is a condition, and here is a condition. As you can see, if at that time, it is just not present in service because it is actually open, so it is inherently like that. And therefore, again, you see that things are fine because it is closed. Okay, if the breaker is open, what is the result? If you open it normally, you just opened it, made it open, and removed your hand so coil A will keep working normally. The DC will go like this and come like that and go to coil B and so on. You will find that this is energized and that is energized, and therefore the trip circuit supervision is healthy because coil C sees that everything is fine. Okay, and if it trips via 94, it's the same thing. But if it trips via 86, 86 means it's a latch, meaning there will be a short circuit in it and the wire is like this. So this wire naturally acts as if coil A won't receive anything. You might say, but the positive is going like this and the negative comes from below. No, once this is shorted, it's a short one on this circuit, so coil A won't receive anything. All right, so coil A will be de-energized and coil B will be energized. And the trip circuit will be for you, what? The trip circuit will be healthy for you. The trip circuit will be for you, what? Healthy. Okay, engineer? Great. So this is the story of what? The story of trip circuit supervision. All right, I've drawn it for you here. I'll go back here again to tell you a story, but let me first finish this circuit with you. So as you can see here, engineer, here's the positive, here's the negative, and here's the trip coil. Before it, there are two contacts, one from 52A and one from 52B. As you can see, the DC comes up to here and exits, then comes up to here and exits, and comes up to here and exits. Of course, you can't see the drawing, or it's not drawn with the same clarity that I explained to you below here. But look with me here. You'll see it in the protection circuits. Here it goes to the protection on a terminal block, enters the contact head, then exits to another terminal block, and so on for the next protection, and so on for the next protection, and so on for the next protection, and so on. All right, boss, until it went to a resistor, or here along with a coil and return. Of course, this connection is wrong. It should go to the contact head and return. Okay, you might agree with it or not, but I'm telling you, from my perspective, I'm saying this is wrong. It should be like this above here, with a terminal block here and a terminal block here, all right? And it should look like this circuit here. Look, see here, it took us to a block, went to the contact and came back. It was supposed to do the same action here and the same action here and the same action here. Engineer Rashad, because quite simply, if I came here and told you this wire is cut, did you see it? No. Why? Because here it is. The positive is moving normally in your circuit. It went to coil A and came back from coil A like this. It returned like this, returned like this, returned like this, and continued normally, completing your circuit. It's not even looking at this wiring, right? Am I wrong? So if this is cut, or this is cut, or this is cut, you have a problem. But imagine with me, if this is cut, it will see it. Why? Because it is supposed to go like this and come down like this, right? Am I wrong? So it will see it, but these won't see it at all. So we need to pay attention to what? To the tricks. All right, engineer, I'm giving you what is 100% correct, regardless of what the witness might request or agree to later. That's not my concern. But I'm telling you what's 100% correct, okay? And here's coil B. As I agreed with you, it goes out from here to coil B with a resistance in series and returns here to this contact. Whether it's A or B, they activate coil A, they activate coil C. I'm giving you the explanation simply as a capsule board.